All right, let's dive deep into a ship's engine room. Today, we're talking about one of the most critical safety measurements on board, keeping an eye on the water level inside a high-pressure boiler.
So why are we so focused on this? Because getting this one single measurement wrong can have absolutely catastrophic consequences. I mean, the difference between a safe trip and a total disaster can literally come down to a few centimeters of water. Let's look at why. You've got two nightmare scenarios here. On one hand, if the water level drops too low, those boiler tubes get superheated and you're looking at a potential explosion. But on the other hand, if the level gets too high, you get what's called water carryover. That's when slugs of water get blasted into the steam lines and they can absolutely shred turbines and other vital machinery. So yeah, there is very, very little room for error.
Okay, so how does the boiler actually talk to the engineers way over in the control room? How does it tell them this critical information? Well, it uses a special language, a super common industrial standard known as the 4 to 20 milliamp signal.
All this really is a way to translate a physical thing, in our case the water level, into an electrical current. It's an incredibly robust and reliable way to send information, especially through the noisy, vibrating, and just plain harsh environment of an engine room. And the relationship is beautifully simple. A low water level, that's a low current, 4 milliamps. A normal happy level sits right there in the middle at 12 milliamps. And a high level, well, that corresponds to the maximum signal, 20 milliamps.
Yep, it's really that straightforward. The amount of current flowing through the wire is directly tied to the amount of water in that boiler drum. More water equals more current. Simple as that.
Okay, now here's where it gets really clever. What happens when the control panel reads this? 0. You'd probably think 0 milliamps means the boiler is totally empty, right? Nope. And this is the brilliant part of the whole design. Because the lowest possible real reading for an empty boiler is 4 milliamps, a reading of 0 can only mean one thing. Something is wrong with the system itself. Maybe a wire broke or the sensor lost power. It's a built-in, foolproof safety check. Just genius. So we know how this signal works, but how do we actually get the measurement in the first place? I mean, you can't just stick a dipstick inside a sealed, high-pressure boiler. That job falls to a very clever piece of equipment called a differential pressure transmitter, or DP transmitter for short. This really is the core challenge for the engineers. You need to know the exact water level inside this big steel can that's full of boiling water and high-pressure steam. So how does this DP transmitter pull it off? It all comes down to 3 really elegant steps. First, it measures the total pressure down at the bottom. That's the weight of all the water plus the steam pressure pushing down on it. Then, at the same time, it measures the pressure at the top, which is just the steam. You just subtract one from the other, and what's left over is the pressure from the water column alone, which tells you the exact level. It's fantastic. But of course, it's never that easy, is it? There's a complication. A boiler isn't some calm tank of water. It's a really extreme environment, and that environment starts to mess with our measurement. We're talking about some serious pressures here, 10 to 20 bar, maybe even higher. To put that in perspective, that's up to 20 times the normal atmospheric pressure you're feeling right now. And that kind of pressure, well, it changes everything. See, under that kind of intense squeeze, the physical properties of water and steam actually change. The steam gets way denser than you'd think, and the water's density also shifts. And since our whole measurement is based on the weight of that water, these density changes can introduce some really serious errors into our reading. So this is where marine engineering gets really, really smart. To make sure the readings are accurate, these systems use some advanced techniques like complex density compensation calculations and special hardware called wet reference legs. These are all designed specifically to cancel out the effects of that high pressure and keep the readings true.
All right, let's see how this all comes together to actually keep the ship safe. That 4 to 20 milliamp signal isn't just for a pretty display on a screen, it's hardwired right into the ship's alarm and safety systems. And this table just lays it out perfectly. If that signal drops to around 6 milliamps, a low-level alarm starts screaming. If it falls even further, down to 5 milliamps, the system doesn't wait for a human. It automatically trips, shutting down the boiler to prevent an explosion. And, the same logic works on the high end, triggering alarms to stop that water carryover and prevent machinery damage.
But even with a system this smart, the real world is messy. Rapid changes in how much steam is being used can cause weird effects like swelling, where the level looks falsely high, or shrinkage, where it seems falsely low. You could even get flashing, where a sudden pressure drop creates a bunch of bubbles and throws the whole reading off. The instruments are just reporting what they see, but a good engineer needs to know how to interpret it.
And that right there brings us to the most important component in this entire safety system, the human being. The technology is an amazing, powerful tool, but it is absolutely not a substitute for an experienced marine engineer.
This is what separates the pros. They have to apply critical thinking. They're constantly double-checking the electronic reading with the old-fashioned must-be-accurate manual sight glass. They understand the ship's conditions that might cause a weird reading, and they never, ever, ever rely on just one measurement to make a decision about safety.
And that really is the heart of it all. The numbers and signals, they're just data. True safety comes from a deep understanding of the physics, of what's actually happening inside that boiler. It's that knowledge that lets an engineer interpret the data correctly and keep that ship and everyone on it safe.